Okay, guys, this is chapter 10. It's the last chapter, and unfortunately, we did the lecture of this chapter last week and this week. But before we start even the lecture, correct? Like part of the experiment we did last week, and we will do this week as well, is titration, acid and base. And this chapter is chapter 9. Is all about chapter chapter 9 is acids and bases. We'll go first of all through three definitions or three types of acids, three definitions or three types of acids. So we have three types of acids and bases. Okay, guys, those three types will be having the names of the scientists that worked on them, correct? So the first type called the Arrhenius acids and bases. So Arrhenius is scientist, so we'll see he started the first definition of an acid and a base. So Arrhenius came up with the idea that any chemicals that dissolve in H2O dissociate in H2O to give me H plus is an acid. Any chemical that dissolves in H2O or dissociate in H2O give me OH minus, this is a base. So let's try to this one. Acid. First of all, this acid, according to Arrhenius, okay, an acid here. Any chemical that can dissociate in H2O to give H plus is called an acid. Okay, guys, so that's what the definition, and you can see this definition is so highly limited. Okay, how about we know a lot of acids and bases, they don't have OHs or H plus. So what we'll do? How we can define them? That's another issue stuff with Arrhenius. But this is a good start, at least. This is a good start. Always we have to start from anywhere or somewhere, and then we can improve this definition. As the time passes through or goes through, we can improve this one through a lot of experimentations and so on. So, can I take this one out? I'll give it. No? Okay, let's finish up. Okay, so we'll now give you an example of Arrhenius with two. One is an acid, one a base, and the acid has to give you H plus, and the base has to give you OH minus. As I said, this is highly limited definition, but still somewhere you have to start with. Something you have to start. Can I take this one out? Okay, now, this one here, if I look at this, I have, for example, an acid such as, this is hydrochloric acid. Okay, this acid here will dissolve in H2O. Let me just, we'll say it can dissociate in H2O here. To produce H plus plus Cl minus, and H2O is just a solvent. This is by Arrhenius is a solvent. this compound here is an acid, it's hydrofluoric acid. So when you dissolve HCl, it's really it's a gas. Dissolve it, gets aqueous, and liquid H2O. So what's happened is this HCl gave you what? Gave you H plus. So plus the chloride ion. So, but the main thing is H plus here, according to Arrhenius, this is an acid by definition. As long as it gives you H plus, that's an acid, according to Arrhenius. A base, on the other hand, KOH, in H2O, again, the H2O is a solvent there. This is, guys, here it is. Let's look at this plus H2O. This is H2O is a liquid. This is aqueous. This is called potassium hydroxide. Hydroxide. We take one of those out, not hydro, and then you pause, and then oxide. No, hydro, pause, and then oxide. No, hydroxide, just one word. Okay, guys. So potassium hydroxide, when you dissolve this one here in H2O, will give you potassium ion, aqueous, plus the hydroxide ion, aqueous, plus H2O, liquid. And this is, again, this is your solvent here. So this is, according to Arrhenius, this is a base. And this is, according to Arrhenius, an acid. That's a definition. And as I said, this is highly limited, but you have to start somewhere, correct? And this is our start in the history of defining acids and bases. So next, now, more sophisticated approach is Bronsted and Lowry. Those two scientists, they came up with more advanced than this. And you will see then our old friend Lewis, who had discovered Lewis dot structure, he came up with even much more sophisticated than all those two definitions. Okay, so the next definition is Bronsted-Lowry definition or type of acids and bases. Can I take this one out? Everybody has it. Everybody has it. I know it's Monday. It's Monday, so therefore, if you don't interact with me, so I can understand. I'm not, not angry or upset. It's Monday. This happened to me too. If I have not taken the big coffee all the way to the top, I told her, all the way to the top, I'll be feeling very bad, or you'll hear my snoring maybe. So anyway, because I was working on a book. We are working on 1151, 1152 now book. So spend all night working, all the weekends, all night. So anyway, but here it is, the definition of Arrhenius. Highly limited definition is not really helping us to go nowhere, but still always a good start. So let's do the second one. Can I take this one out? Everybody has it? Okay, let's take this one out. Let's do the second one, which is much more good one and still used, but again, is you will see the Lewis is more advanced than this one here. Bronsted and Lowry acids and bases. Gesundheit. You said bitte sehr, or gleichfalls. So, well, Bronsted said now we have, remember Irina said it's dissolved in H2O, correct? They said, no, we have, okay, that's dissolved in H2O, it's a good idea. But we say it dissociates in H2O, and the acid will, during this dissociation, will donate its proton, correct, to the base. The base will accept, okay? So the principle of acid base is donor, acceptor, double C, sorry, acceptor. It is uh, uh, principle. So tell you that the acids are donating their H plus. Now H plus does not really exist. We say not really. Does not exist. H3O plus. This is called hydronium ion. Their hydronium ion. H plus is not exist. It's not there because H plus aqueous plus H2O. You have always this is in the solution. So this is liquid. You have this one here in the solution, aqueous. This one here is hydronium ion. So acids are donating. This is one. Second one, bases are accepting the hydronium ion. So that's hydronium ion. This is the definition of what of of the roasted Lowry. So we'll go and look in specific ones. No, because we did not mention H2O, but we have to add H2O in the definition itself. Can I take this one out? But at least acids donating and the bases. Bases here, guys. Sorry. Bases are accepting. So now, can I take this one out? Everybody has it? Okay, everybody has it? Yes, no? Okay, yes. So take this one out. Now, Ronsted and the Lowry, they said, okay, let's look at this. If I have an acid, it has to be dissociating inside H2O. Otherwise, the whole thing is not possible, correct? Has to dissociate in H2O first. This is first. After this dissociation, this will have what? It will have a plutonium. This dissociation here reduces our what? Hydronium ion. This is hydronium. Number 3, now the acid, as soon as it's forming its hydronium ion, is now the acid now can donate its to the base. Okay, so that's a good definition of of what we have, and that's the theory is still valid. Arrhenius' theory is about acid base is obsolete. Nobody's using it, but this theory is good. So now, if I said about this acid, okay, so I can take this definition here and do it for the base, correct? So I will say here it is. So I can give you an example first before we go further. So I have nitric acid. Nitric acid, aqueous. That's an acid. This is nitric acid. Nitric acid, you add it to H2O, correct? So this is liquid. And the first thing is you have to produce H plus aqueous. Hydronium ion. This is your hydronium plus this is hydronium ion plus NO3 minus aqueous. So it looks like this is acting like an acid. This is acting like a base. The H2O is acting like a base. This is acting like an acid. Okay, guys? So with this in mind, we can strike. Okay, so now I can define the base, correct? This is accepting. So you take an acid out, say a base has to dissociate in H2O first. That's very important. And this is not the case for a base. Does not produce H2O, but the base now can accept the hydronium ion from the acid. Correct? So we defined the green color notes are for the base. So the base has to dissociate first, makes itself ready, and then when this dissociate, it can accept this hydronium ion from the acid itself. Let me just show you here. Okay, guys, so it is this dissociation of H2O, but sometimes it's acting like a base. So here it is. Can I take this one out? I'll make an example here. I'll make an example. Can I take this one out? Okay, let's take an example here. Show you an example. So we'll take a base, which is took nitric acid, for example. Nitric acid with H2O would produce first its hydronium ion, correct? Hydronium ion can react plus nitrate, of course. Will give you hydronium ion, then will come to the potassium hydroxide. That's a base, correct? Everybody's following here? So this here, hydronium ion, will come and add itself with OH. So you get out of this, if you look at this, you get the acid is accepting this, and it will have potassium will come by itself, aqueous, 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 liquid, aqueous, aqueous. So, and you get out of this H2O, correct? You get out of this HU. I did not balance this, but show you how the whole thing is. So if I have the reaction here, just show the reaction here. Nitric acid plus potassium hydroxide will give you potassium nitrate plus H2O. Okay, guys, this is negative. So if you take all this here, this is aqueous, and let me just put this one here. So KNO3, aqueous. This is liquid. Now, if this is complete what molecular complete molecular ionic chemical equation. Complete molecular ionic chemical equation. Now I have to take, or not ionic, this is just a complete without ionic. We'll make the ionic one. Complete molecular, complete chemical equation. So chemical what? Chemical equation. It is chemical equation. Now I want to make the ionic one, complete ionic. I have to take both reactants and products apart, which is having ionic aqueous. All of them aqueous except this one liquid. Liquid and solid are kept by themselves. This one will be H plus aqueous plus nitrate aqueous plus potassium aqueous plus OH minus aqueous gives you potassium aqueous plus nitrate aqueous plus H2O liquid is not taken apart. Now the net ionic here, the net ionic chemical equation will be, take the spectator ions out. We talked about this a long time. I hope you are still remembering it. So which those spectator ions, they appear on both sides. So I have nitrate here, reactants, nitrate products. So nitrate out. I have potassium reactants. I have potassium product out. So really the reaction of an acid base is really the reaction of the protons, which is hydronium ion, plus OH minus, give you what? H2O, liquid. This is aqueous, this is aqueous. This is the net ionic chemical equation. The driving force of an acid-base reaction is the production or the formation of H2O from the donation of the acid with the hydronium ion. Here's just a protonium ion. So, okay, guys. So that's the acid-base donor. So the acid will give this one here. I mean, you can just name it. This will be hydronium ion. So, okay, guys. Everybody's following? Okay, so this is number 2. Number 3, we have Lewis acids and bases. Lewis acids and bases. Okay, so we have Arrhenius. Just Arrhenius will tell us dissociation, bring you the protons. That's acid. Dissociation brings you OH, hydroxide, ion. This is a base. The Bronsted Lowry, they went a little bit further in depth. They said no, this has to do with the donor acceptor process, as the acid will donate its protons or hydronium ion, and the base will accept this proton or hydronium ion. Now Lewis said, how about compound or chemicals? They don't have a proton at all. What you can tell about those? They have nothing there. So what you can tell about them? But we know when we test them in the lab with the litmus paper, they can be tested as acid or acidic or basic or neutral. So and therefore he came up with the idea of um, valence electron donor acceptor instead of the hydronium ion or the proton donor acceptor principle of Lewis and Lowry, of Bronsted. He came up with his own valence electrons electron donors. So it means valence electrons. Can I take this one out? Now, the third type is our friend here, Lewis acids and bases. It came if a chemical has surplus of valence electron, correct, especially if they are non-bonding, so they are and they have the ability to donate those. So let's start with the base. A base is a chemical that has surplus or extra VEs, which can be donated. Okay, so you'll ask yourself, how in the world I would know this is a Lewis acid or base? Well, let's look at this. I have ammonia, correct? Ammonia Lewis dot structure will tell you this is a Lewis dot structure of ammonia, correct? Therefore, Lewis came to the idea, if I have those are here, so then I have this here. Those are surplus, correct? The other valence electrons are bounded and they are forming a single or double, triple bond. In this case, we have 3 single bonds. Ammonia has how many? 3 single bonds. But those are here by themselves. Those are surplus. Those are extra. Those are what? Those are extra VEs, valence electrons, correct? So now, if this will be able, those can be donated, correct? So therefore, ammonia is ammonia is acid or base? No, according to Lewis said ammonia is a base. Why is a base? Okay, well, it has extra what? It has extra valence electrons. Can you see it? It has extra, can be donated. Now let's look at the donation to any acid or any acid we can think about. So can I take this one here? So those can be donated. Now the base, on the other hand, is just the opposite of whatever we have. They are what? VEs deficient. They are valence electrons what? Deficient. They don't have that much of valence electrons, or they available, correct? That's extra here. That's extra here. How about H2O? We'll talk about H2O, but the same token, if I have H2O, what you can see, H2O can very obviously be considered as a base. Why? Because it has surplus of valence electrons not connected to any bonding, correct? We have 2 single bonds and 2 lone pairs. Those lone pairs can be considered as a base. Now we'll see later on H2O can act amphoteric, can act as an acid. That's very unique for very few compounds in chemistry. Not every compound will act as an acid and base at the same time. No, but the dual character of H2O and very few other compounds, they can flip flop, can be acid or base depending on their reaction. But here you can see it is very obvious that H2O is a base. Has to be a base, has to act a base because it has those VEs not really involved in any bonding, so they are available. So they can be donated. Those can be donated. Those VEs here, non-bonding lone pairs can be donated. And the same thing here. Those and those can be donated. Correct, guys? So H2O is a base here. H2O is a base. Now, as I said, H2O can act as an acid as well. Can act as an acid as well. So, okay, guys. But the main Lewis definition of an acid or base is the surplus of valence electrons. If that compound has a lot of available VEs, so they can be donated, then yes, this is a base. If the other side, the other hand, the acid has deficient, correct, has deficient valence electrons and cannot, so they can accepting those valence electrons. Okay, guys. So that's the definition of acid base according to Lewis. So we'll do some examples here. So can I take this one out? Everybody has it? Everybody has it? Everybody has it? Okay. Now, some compounds you'll be astonished to see they are like aluminum oxide. If you test aluminum oxide is acting as an acid. Well, aluminum oxide, this is acting as an acid. Although the oxides are most of the time they can be can act as an acid because it's electron deficient. VEs valence electron deficient, so it can act as an acid. Okay, so can act as an acid. Although the oxides are bases. Oxides in general are bases. But aluminum oxide, because it's deficient, can accept valence electrons. Another example of this is BF3. So when you let BF3 react with ammonia, this one has this. So what's happened will be, what do you think is happening? Can you tell me what's happening? Somebody will tell me what will happen? Well, this one here has extra VEs, correct? So this one, according to Lewis, is what? It's a base. Can donate those two. So then you will have boron trifluoride is looking like this. Oops, sorry. Let me just. Boron trifluoride with ammonia, the fluoride here so here it is. So what you can tell about this, of course, the boron is, if you look at the This one will be negative charge. This one will be positive charge. So, but this is typical donation of see here. This is an acid now. Is what it's deficient is V is deficient. So this is it's not does not have two extra here. It's not. There's no valence electrons here in bromine. And if you look at this, BF3 is looking like this. The BF3 is has no, not this. Let's take another color. This is boron trifluoride. Lewis dot structure. The fluorine has 7. One is making single bond with boron. So this is the Lewis dot structure. So does not have extra or surplus extra at central atom. We are looking always central atom. Extra V's on central atom. So if it's not, then it's this central atom is electron deficient, and by definition of Lewis, this molecule will act as an acid. Anytime I have the molecule has at its central atom extra of those V's, this molecule will act as what? As a base. Are you following me here? Another example. I'll give another example, organic one. So you get the idea how this look like now. Can I take this one out? I'll give some aromatic compound that's very obvious. Can I take this one out? And this is typical for any compound that has nitrogen. Nitrogen is well known, and oxygen. They have extra what? Extra valence electron in their central atom. Can be used, can be donated. When they start donating those VEs as here, see those are the 2 electrons here. The 2 electrons of those here, the 2 here, is coming here to make this bond, single bond between boron and nitrogen. Those are the 2 here. So therefore you have this type of compound. Now, can I take this one out? Everybody has it? Everybody has it? Let's take this one out and look at another example. It's not, you don't have to worry about this. A little bit more advanced organic chemistry, but here it is. It makes this. It is. I have to be an artist here one day. So we have triple bond, and here we have in the middle here we have nitrogen. Okay, and this compound is called pyridine. It's highly toxic, a highly toxic compound, and it has what? It is. So this is according to Lewis is what? Acid or base? What do you think? According to Lewis, it's a base because it has extra. This is Lewis base. But Bronsted cannot and Lowry cannot tell you anything about this compound. Are you following me here? It does not have protonium ion to donate or accept it. If it's base, it has to accept a protonium ion, but it does not have any protonium ion. It's H2O insoluble. It's not soluble in H2O, and that's what the limitation of Bronsted and Lowry. Always aqueous solution. They have to dissociate first. The acid has to dissociate first in H2O to produce this hydronium ion. But here Lewis solve for us the mystery. If the compound is does not or is not soluble in H2O and does not have any hydronium ion, therefore, or cannot produce any hydronium ion, we are looking for the extra VEs at the central atom. So nitrogen, this one had VEs by itself, service base. Now, if I have a compound now that's deficient, does not have at central atom any, correct? That can give you bless you. So the same compound here, BF boron trifluoride, correct? So three and here. So if you look at this, this is so now you'll see that the product will be astonishing to see. The product is, or here you can do it here. So the product is the donation of this 2 electrons here, 2 valence electrons, and you will see the compound will be looking this is will be positive. Nitrogen will be positive. This one probably will be negative. So let me maybe put it inside the ring so the nitrogen will be positive and boron will be negative. See here, that's the donation of the valence electrons. That's the donation. Those are donated to the boron. This is the compound. You don't have to worry about it, but I want to show you how they are donated. Any question about the three types of of acid and bases definitions? Okay, guys. As I said, Lewis is really completing the whole picture of the definition, because some compounds you'll never know that they are, because they are not soluble in H2O, but they can be acid or base. So how we can know they are acid or base, correct? So the only thing you can know is just looking at the valence electron, extra valence electron available at the central atom there, or at the molecule itself. So can I take this one out? Take it out? Okay. Next is to look at the definition of the called the conjugate acid and conjugate base. So if I have HCl and this is aqueous, this is an acid. By now, according to Arrhenius, it has H plus. Well, we know that's dissociative to give H hydronium ion, correct? And HCl, and we will add to it H2O liquid, and we have here, if you look, H3O plus aqueous plus Cl minus aqueous. Now, what's happened is, according to Bronsted and Lowry, this HCl an acid and H2O act as a base, because this one here will be donated to H2O. Then you see here, this is like looking like H2O, correct? So that the donation of the hydrochloric acid, the protons, to the base. The base is accepting, H2 is accepting, so it's acting like a base. Anytime a molecule or compound accepting the protonium ion, hydronium ion means, therefore this is the will be considered as a base. So now this is acid and base, and the H3O plus, the hydronium ion, is recognized as conjugate what? Conjugate acid. And this one is recognized as conjugate base. Now ask yourself, what is conjugate acid or base? Well, the definition is telling us that the conjugated acid, it was a base to begin with, correct? It was a base. Okay, it was a base. Now, it was a base. But now, it accepts H plus. Okay, now it's becoming what? Conjugate acid. What is a conjugate acid? It was really a base that's accepted H plus and becomes a conjugate acid. So a conjugated base, it was an acid because that last, so it's HCl minus with H, it was an acid that last H plus. So therefore we will have two definitions together. We'll say, okay, this is connected to this, and this connected to the other one. We call this one here acid and its conjugated base, the top. This is acid with conjugate base, and this is a base with conjugate acid. Okay, guys, would like to because this will come in the next exam and quiz and in the final exam. So look at we can review this one here by looking at one of the worksheets there to see if we can determine. So what is a conjugated acid? What's a conjugate base? A conjugated acid, it was a base that's accept H plus. A conjugated base, it was an acid that lost H plus. So let me look at the worksheets here and see if we can solve this. Can I take this one out? Okay, everybody has it. So let's see here. I think I have for you maybe we have to look at the iCollege together. Maybe we have to okay, let's see. Okay, let's look at this. Chapter 9. Let's look at worksheets if we have worksheets here, PowerPoints, Station, SigFix, worksheet chapter 9. Let's download it. Okay, it's there. And we'll look at this because this is very important. Students are very confused. Which is a conjugated acid? Which is a conjugate base? What is a conjugated acid? So it's done. See if it's in download folder. Yes, in download folder. So cut it here and paste it into desktop. Okay, so this is a zip file, so it's not helping that much. So I have to copy it out. Here it is. Now it's easy to open. Paste it. Okay, so now let's look at this. This is an iCollege, guys. So you can just download it and so acid base. Let's see if we can see a conjugate. Here they are. See here. See acid base and conjugate acid and base. We need one without the key, without answers. So let's see here. Otherwise, we'll see. I put you some of them with the answers. So, well, those are just YouTube answers. So it's not helping us that much. Key. Okay, that's a good one. That's a good one. No answers, I hope. Yeah, that's a good one. There are no answers. This will be a very good one. There is a good one here. So now you have to identify for me acid, base, conjugate acid, and conjugated base. So we'll have just from A to, wow, from A to F. So let me just reduce the, so we can have all those together. Yes. So, wow, there's too many of them. So let me reduce it further so we can have most of this one here. So, okay, guys. So we have from A to H. So select two and tell me. We have to identify. That's an ACS exam. That's the final exam will come. You have to identify sometimes the acid, sometimes the base, sometimes, most of the time, they ask for conjugate acid and conjugate base. So let's have two of them here, and then you can try practice a couple of those. This is in iCollege. This is a very good worksheet here, and the good thing without answer. That's the main thing. So then you can ask for. Now they have the answer, so they have the answer, but don't look at the answer at the beginning. Don't look at the answer. So let's take one of those. Two. I will have my snipping tool ready to go here. So which one you like from A to H? Which one? Any preference? B? Okay. Okay, so somebody said B. Okay, so let's see. Okay, so now, where is the acid? Where is the base here? Somebody will tell me. Where is the acid? Where is the base? According to Lowry and Bernstein, correct? Acid always dissociates in H2 and be able to donate its proton or hydronium ion. The base, on the other hand, dissolves in H2O, dissociates in H2O, and accepts this donated protonium ion or protons. Correct? The conjugate acid was a base to begin with that had accepted the proton ion, and the conjugated base, it was really an acid to begin with, but it had lost its what? So which one of these is donating an H plus? Which one is accepting? Come on, guys. I know it's Monday. I can understand this. Don't worry about it. I know it's Monday. So have a sleep, myself too. So this is we have sulfuric acid looking like this. We'll come to name those acids later. This is sulfuric acid. Sulfuric acid. Now, if you have less one oxygen, H2SO3, like the one you have here, this will be sulfurous, OUS, sulfurous acid. So that's sulfurous nitrous. Okay, so fluorous. So here it is. Which is donating? Come on, guys, don't let me. This one, how many hydrogen does it have? Now, how many here? One. So this has to be what? The acid, because it's donating. One is proton. One here is not appearing the other side. The other side is showing that it had lost one of these protons. So the H2O then accepting this, it has instead of 2, how many? 3. So it's accept. This will be base. So this one here is donates H plus. Now H plus does not exist, but this H3O plus, and this one is accepts H plus. Of course, H plus here, remember this is H3O plus. That's what you mean. And I told you this is H plus, it does not exist, it's not present inside the solution, it's dissociate with H2O to give you H3O plus. But we just for the sake of the simplicity, so we just put H plus, but really it's hydronium ion, because as soon as H plus is formed, it dissociates with H2O to give you. This is present in solution. Okay, so we figured out the acid and we figured out the base. How? Well, we looked at the one that's losing H, the losing proton or hydronium ion. Well, this one had lost. See here, only one here. So this one has to be the acid. Which one is accepting? Look at this. This is 2 hydrogens, correct? Now, how many we have here? 3 hydrogens. This one has to have accepted extra hydrogen, correct? So this is a base. Now, what we call this one here, conjugate what? And this is conjugate what? Now, conjugate HO3 plus, conjugate acid or base? Now, somebody said acid. Let us open an option here. No? No? Well, I was watching this weekend, one of them. An auction for the cars. And this was very funny. I mean, somebody does not want even the car itself, but scratches the hair. It's sold for you. It's sold. The guy cannot say no. It's your price. Anyway, so what we call this one here? A conjugate, let me repeat. A conjugate acid is the opposite. It was a base that had, correct? It was a base that had gained H plus. A conjugated base, it was an acid that lost H plus. Make sense? So the conjugate, this one will be a conjugated what? Acid. Why? It was a base. It was a base. It was a base. It was what? A base that accepted H plus. Now it's accepting, it was a base, but now it's accepting what? Okay. Here. It was a base, correct? But now it is accepting, it's accepting H plus, correct? How about the other one? Conjugated what? Base, correct? Because that's like a dual pairs. If you have an acid, you have a conjugated base. If you have a base, you have a conjugated acid. So this is conjugated base. So it was what? It was an acid, correct? But now it's losing, now it's losing it's H plus. Makes sense, guys? Okay. Okay, let's see. Let's hope for the best. I know it's still Monday, still Monday, still Monday. We are not out of it yet. So let's take this one out. Can I take this one out? Let's do another example. Let's do another example. Okay, so let's do another example. Which one you like? We did the B. I need the other side. The other side. Don't sleep on me. The other side. The left side. The left wing of the class. Come and select. Always the time. The active ones are the right wing. The left wing of the class is almost half asleep or something. So which one you like? The left side. Come on, guys. I did not hear any snoring yet, but everything like almost in this direction. So select one of those here with the right side of the class, the right wing class of they chose or they have chosen the B. So what do you like? Except don't include the B. The B is already taken. Which one? From A, C, D, E, F, G, H. Which one? Come on, guys. Yes. C? C. That's, sign language? No? Yes? Yes? No? Okay. I have a daughter, she's 39-year-old, so she's deaf. She was born 39 years ago in Missouri, Kansas City, Missouri, Kansas City 2 of Kansas City. Kansas City, Kansas, Kansas City, Missouri. Or Missouri, they call it Missouri, so. But anyway, so I learned the sign language, so. Now, how many language? My native language, English, German, and sign language. Yes? Yes. Okay. Thank you. Okay, so she said C. We'll go for C. Okay, we'll go for C. Okay, that's my snipping tool. Copy. I'm copying this snip. Then I go to this, highlight this, take it out, and paste the new one. C. So now, you tell me which one had lost the. Now both wings can contribute. The selection is I wanted the right wing to work with me. So both of you now, both wings, right and left. So you tell me which one is losing proton, H. That will be our acid, correct? Which one? Come on, guys. Yeah, which one an acid? Because acid and base will be only on one side. And then conjugate base and conjugate acid the other side, correct? So acid and base will be always, we consider always reactants. And the conjugated base and conjugate acid will be our product. So we know that now they are conjugate. So they are our products. They have to be so now we know that's by definition always our products, correct? But sometimes the question will not go like this. Sometimes we'll give you, as you'll see, one of those examples, challenging exam, they will give you two pairs, and then you have to tell which one conjugate. They can form conjugate acid conjugate acid pair. So, but this is a good idea to look at the whole chemical reaction. Which one is an acid? This is acetic acid. This is titration we did with the last week. Vinegar. This is vinegar, acetic acid. This one here is acetic acid, or called ethanoic acid. So acetic acid, correct? So it lost what? This one is gone, correct? Where is it? It's gone, correct? So this is an acid. Why? Lost H plus, correct? This has to be if this by definition has no other way. If one is you have figured out the acid, the other one has blindly, without even looking, has to be what? A base, correct? A base. So why? Because one is losing, one is gaining. So gained, lost, and gained H plus. Okay, guys. So gained H plus. So how many here we have? Two hydrogens. How many we have here? Three. So that's gaining, correct? Okay. So and here is one is here is H is missing, correct? Here H is present. The other side is missing. So what we call H3O plus, a conjugate acid or a base? Base, why? But you have it already here by definition. We said H2O is a base because it's accepting one proton. It's a base. So a conjugate acid, you said conjugate base. What is a conjugated base? It's an acid that had lost H plus. So this is a conjugated base. Whoops, yes, whoops, we can say whoops very loudly. So it's Monday, I know. This is conjugate acid. Everyone's following? It is a base. It was a base. It was what? A base. And this is very important. And here it was what? An acid. The opposite, whatever it says here, base, but it was an acid here. No, that lost H plus. Make sense? Okay, so any question about this? Any question? Okay, so let's go further, and I hope that we can. 3 minutes. I don't want to have a topic. We wanna go and name those acids and bases. We wanna see their reactions. We wanna see the buffer, the pH. This is a long chapter, and I have really have written this chapter by myself, so I'm working on editing it again. So here it is. Let's look at the maybe another one. Let's look at the one with the keys. So here, guys, can you see that? Can you see the answer? This is an acid. Oh, sorry. See, with the answers. This is an acid. Why? Because it has this one here. Now, this acid is lost. What? Is lost its proton. So it was an acid. It has to be conjugated base. It was an acid. See? It was here. So this one here called acid conjugated or conjugate base pair, and the other one we have base and conjugate acid pair. Correct, guys? So this one with this, and the other one with this one here. This with this one here. Okay, guys? So those are the questions. They have the answers there, so you can look at their answers. So any question? Any question? One more minute, just to look at another one. Quick. And those are the same thing. So, but anyway, so I'll see you then this coming Wednesday to look into the definitions and the naming of this acid. Thank you.